Namaste dosto. Imagine you are in your room and you want to describe exactly where your study table is placed. You don't just say next to the wall, you want precise directions. That's where three-dimensional geometry comes in, helping us pinpoint positions in space using three mutually perpendicular axes. In this system, we have the x-axis, the y-axis, and the z-axis. Think of them like length, width, and height, the three directions you can move in a room. The x-axis runs left to right, the y-axis goes forward and backward, and the z-axis points up and down. Every point in this 3D space is represented by an ordered triplet. We say it like this: open bracket x, y, z close bracket. This means you give three numbers at the position on the x-axis, the y-axis, and the z-axis. It's like extending the two-dimensional graph from the Cartesian plane by adding height. All three axes intersect at a special point called the origin, written as O0, 0, 0. Each coordinate tells you the sign distance from each axis, meaning it can be positive or negative depending on the direction. This system is called the rectangular Cartesian coordinate system in 3 dimensions. It's the foundation that lets us navigate, plot, and calculate everything that exists in 3D space. Allez va! Isn't it fascinating how this simple idea helps us make sense of our 3-dimensional world? Now that we know the 3 axes, let's explore how they divide space. Imagine slicing a loaf of bread with 2 cuts. That's sort of like how the coordinate planes work in 3D. These planes are formed by pairs of the coordinate axis. The xy plane combines the x and y axis, the yz plane combines y and z, and the zx plane combines z and x together. These 3 planes split the entire space into 8 parts called octants. Each of these coordinate planes contains all the points where one coordinate is 0. For example, the xy plane includes every point where the z coordinate is 0, like a flat sheet lying horizontally. Here's a quick example to understand an octant. Consider the point with coordinates open bracket -3, 2, -5 close bracket. This means x is negative, y is positive, and z is negative. So that point lies in the octant where the x-axis is negative, y-axis is positive, and z-axis is negative. Keep in mind, the numbering or naming of these octants can vary depending on context and is not standardized across all boards. But conceptually, knowing how the coordinate planes divide space is very important for visualizing points in 3D. Moving on, suppose you want to find the distance between 2 points in 3D space. Just like in 2 dimensions, where you use the distance formula, here we extend that idea by adding the third coordinate. Let's say we have 2 points, point P with coordinates x1, y1, z1, and point Q with coordinates x2, y2, z2. The distance between them is given by the formula, the square root of open bracket x to minus x1 squared plus y to minus y1 squared plus z to minus z1 squared close bracket. Let me repeat that slowly. The distance PQ equals the square root of open bracket x to minus x1 squared plus y to minus y1 squared plus z to minus z1 squared close bracket. This formula comes from applying the Pythagoras theorem in 3 perpendicular directions: length, width, and height. And what it gives us is the length of the straight line, the shortest path, connecting the 2 points in space. This distance calculation is very useful not only for measuring lengths of edges or sides but also in vector magnitudes and checking conditions like collinearity. Shabash! You are getting the hang of 3-dimensional calculations. Let's explore something a little trickier, the section formula in 3 dimensions. Imagine you have 2 points P and Q in space, and you want to find a point R that divides the line segment PQ in a given ratio m to n. When this point divides the line internally, its coordinates are given by open bracket m times x2 plus n times x1 divided by m plus n, m times y2 plus n times y1 divided by m plus n, m times z2 plus n times z1 divided by m plus n close bracket. To say it clearly, the x-coordinate of R equals the sum of m times x2 and n times x1 divided by m plus n. Similarly for y and z. For external division, the formula is similar, but the signs associated with m and n change according to the type of division. The main idea remains to interpolate the position of R along or beyond the line segment joining P and Q. This formula extends the familiar 2D section formula by including the z-coordinate, which is crucial for 3D problems. You'll find this very useful while deriving centroids, incenters, or working with vectors where you need scaled position points. Allez va! We just moved from 2 to 3 dimensions smoothly. Here's a simple but important special case of the section formula, the midpoint. When a point divides the line segment exactly into 2 equal parts, the ratio m to n becomes 1 to 1. The midpoint m of points P and Q is given by open bracket x1 plus x2 divided by 2, y1 plus y2 divided by 2, z1 plus z2 divided by 2 close bracket. This means you just average the corresponding coordinates of the 2 points. The midpoint represents the geometric center of the line segment. It is often used as a position vector tool in problems involving symmetry, centroids, and dividing diagonals. So next time you think of dividing a segment exactly in half, just remember this neat averaging formula. Excellent beta. Now, how do we check if 3 points in space lie on the same straight line? This is the concept of collinearity in 3D. Suppose you have 3 points A, B, and C. The points are collinear if the vectors from A to B and from A to C are linearly dependent, that is, if one vector is just a scaled version of the other. In simpler terms, the direction ratios of vector up and vector AC must be proportional. Using coordinates, this means the ratio of x to minus x1 to x3 minus x1 equals the ratio of y to minus y1 to y3 minus y1, and also equals the ratio of z to minus z1 to z3 minus z1. Put plainly, if all 3 of these fractions are equal, then points A, B, and C lie on the same straight line. This check avoids the need to plot points and is critical for theoretical proofs and coordinate-based geometry problems in 3 dimensions. Shabash! Let's quickly recap what we've learned today. A point in space is represented by coordinates open bracket x, y, z close bracket. The distance between 2 points uses the formula square root of open bracket x to minus x1 squared plus y to minus y1 squared plus z to minus z1 squared close bracket. The section formula lets you find a point dividing a segment in ratio m to n with coordinates open bracket m times x2 plus n times x1 over m plus n, and similarly for y and z. Remember, the origin point is 0, 0, 0. The coordinate planes divide space into 8 octants. Direction ratios help in checking if points lie on a straight line. And throughout, we've extended familiar 2D formulas by adding the z component for 3D. Soch ke dekho, all these ideas give us powerful tools to navigate and analyze 3-dimensional space, which is key for your future exams and beyond. Stay curious, keep practicing, and shabash for making it this far.